You may already know that, in quantum physics, a particle can exist in a superposition of states, meaning it doesn't have a single definite position or condition until it is measured. In that state, it behaves as if it's in many possible places or states at once. But despite decades of research, scientists still don't fully understand what superposition really is. What is the particle actually doing while in that superposition? What does that in-between state look like? And perhaps the deepest mystery of all, how does the particle know where to appear the moment we make a measurement? How does reality decide on a single outcome from infinite possibilities? These are still some of the biggest questions in quantum mechanics, and no one has clear answers yet. But recently, a groundbreaking quantum experiment has stunned scientists by offering new insights into these mysteries, possibly revealing hidden aspects of reality that were previously beyond our understanding. This discovery might bring us one step closer to answering some of the most puzzling questions in physics. So let's dive into this latest breakthrough that could change the way we think about the universe itself. We've all heard of quantum entanglement, right? Quantum entanglement is like having a pair of gloves, one left and one right, that you put into two separate boxes and send to two different places. You don't know which glove is in which box. But as soon as someone opens one box and finds the left glove, they instantly know the other box has the right glove. In normal life, that makes sense because the gloves were already left and right from the beginning. You just didn't know which was where. But in quantum physics, it's stranger. The gloves aren't decided until one is opened. Before the measurement, each box doesn't contain a specific glove. They're in a kind of fuzzy state where both left and right are possible. The moment you check one, the other instantly becomes the opposite even if it's far away. That's quantum entanglement. Two particles connected in such a deep way that measuring one instantly defines the other, no matter how far apart they are. Einstein called it spooky action at a distance. Now here's where it gets really weird. Recently, scientists tried something completely different. They asked, can two particles be entangled if they don't even exist at the same time? At first, this sounds impossible. I mean, how can something in the future affect something in the past? How do you entangle something that hasn't even been created yet? But quantum physics, as always, doesn't care about what feels possible. Here's what they did in this experiment. In a fascinating quantum experiment, using lasers and special nonlinear crystals, researchers generated a pair of entangled photons at time t1. Let's call them photon 1 and photon 2. At the moment of their creation, photon 1 and photon 2 were entangled, meaning their properties were deeply linked. Photon 1 and photon 2 then went their separate ways. However, shortly afterward, at time t2, photon 1 was measured and ceased to exist. It's because in quantum experiments, where measurement collapses the particle's state, photon 2, on the other hand, continued along its path after being reflected by a mirror or beam splitter. Later, at time t3, scientists generated a second pair of entangled photons, photon 3 and photon 4. Now here's where things get really interesting. At time t4, scientists performed a special quantum operation known as entanglement swapping. They brought together photon 2 and photon 3 and performed a joint measurement on them. This operation effectively transferred the entanglement from the pair 1 and 2 and the pair 3 and 4, so that photon 1 and photon 4 became entangled. Even though they had never interacted directly, and even though photon 1 had already ceased to exist long before photon 4 was even created. Finally, at time t5, when scientists measured photon 4, they found that its quantum state was perfectly correlated with the earlier measurements of photon 1, as if the two had been entangled all along despite existing at completely different times. This result is astonishing because photon 1 only existed between T1 and T2, while photon 4 only came into existence after T3 and was measured at T5. Yet due to the entanglement swapping process, they behaved as if they had been part of the same entangled pair. What this tells us is profound. Entanglement isn't limited by time. It doesn't require particles to coexist. Instead, quantum mechanics simply cares about correlations, relationships between states regardless of when or where those events occur. So does that mean the future can affect the past? Well, not in the everyday sense. You can't send a message to your past self or change history. But at the quantum level, the correlation structure seems timeless. The wave function is flexible in time and space. What matters is the full experimental context. By the way, the real question is, how does nature arrange these correlations across time without rewriting history? That part remains mysterious. Main interpretations of quantum mechanics like Copenhagen, many worlds, pilot wave, don't give a satisfying narrative for this. They simply calculate probabilities and move on. But hold on. Some scientists now think that the answers to these questions might be connected to the way time actually works. In a recent study, researchers found some unusual things about the nature of time itself, and these results could help explain some of the biggest open questions in quantum mechanics. We all know that space has 3 directions: up, down, left, right, and forward, backward. You can move in any of those. But time? Time seems like a one-way street. You're born, you grow up, you age, and that's that. You can't sidestep into Tuesday or climb into next year. But what if that's just how it feels to us, not how it really is? Some physicists now think that time might be like a big 3-dimensional field. You and I just happen to experience one narrow path through it, one direction. But reality might be way more complex behind the scenes. According to the 3-dimensional time theory, time has 3 independent directions, typically imagined as 3 axes of motion similar to the spatial X, Y, and Z axes. In the X direction, you're walking forward through time. This is your normal experience of life, moving from past to future. Moving in the Y direction could mean exploring alternate possibilities, different outcomes of an event during the same time period. And the Z direction could represent internal time, such as subjective experiences, memory flow, or layers of consciousness. Imagine you're walking down a straight path in the X direction. It's like moving forward and experiencing time as we normally do. Now imagine another path that crosses this one, going sideways or in the Y direction. If you could step onto that sideways path while remaining in the same moment of regular time, you might find that things are slightly different, perhaps a different version of the same day. Moving along this perpendicular second path could allow you to explore different outcomes of that day, without going backward or forward in time as we know it. The existence of those different outcomes corresponds to the second dimension of time, while the ability to shift from one outcome to another is what the third dimension of time makes possible. In this theory, there are directions in time we just don't experience. Let's call them sideways time and up-down time. We can't walk through them, but particles in the quantum world can. When a quantum particle is in a superposition, means that mysterious state where it hasn't yet decided what it is. It might actually be exploring different directions in time before settling on a definite state. It's as if the universe gives it room to try out all the possibilities. Then, when we measure it or observe it, that's like locking in one of those paths. This idea also helps explain strange quantum behaviors, like entanglement, or why particles sometimes seem to know in advance what outcome we're going to observe. Maybe it's not magic or fate. Maybe the particle has already explored that path through other, hidden directions of time we just can't see. Now let's put it all together. On one hand, we've got experiments showing that quantum entanglement works across time. 2 particles that don't exist at the same moment are still deeply connected. On the other hand, we've got this new theory that time might be 3-dimensional, giving particles the freedom to travel or connect in ways we can't see. And when you combine both ideas, a stunning picture of reality starts to form. It also touches on some of the biggest unanswered questions in quantum physics, like what a particle's superposition state actually means, and how or why it collapses into a single outcome when measured. According to these experiments, when a particle is in superposition, it's not stuck between choices. It's actually exploring different possibilities in different directions of time that we can't see. It might be reaching into a sideways part of time, where multiple versions of events play out in parallel. And just like entanglement across time connects events from the future and the past, superposition might be the particle's way of staying connected to a whole range of outcomes, not only spread out in space, but also across these hidden parts of time. Then, when we measure it, we're not forcing it to decide. We're just entering the picture at one particular angle, one direction of time, and from our perspective, we see only one outcome. But behind the scenes, the particle may have already explored many paths through extra time directions, and the result we see is the one that fits both the past and the future in a consistent way. It's like the universe picks the path that keeps everything in balance. Reality might be fundamentally about connections, not just in space, but across a richer, more intricate temporal geometry than we've ever imagined. We don't live in a rigid timeline. We live in a network of potentialities. That's the end of this video. If you found it interesting and informative, let us know your thoughts in the comments. We'd love to hear from you. Also, if you'd like to support our work, you can do so by purchasing our t-shirts or donating via Super Thanks. Your support helps us create more amazing content. Thank you for watching.